Thank you very much, Riddhi, and the other organizers for the invitation. It's been really a great pleasure to be here. I should first apologize for the title. I hadn't realized the conference would be so specialized, so this became a bit pretentious to talk about this such a broad topic. So this is a tentative plan of the talk. So I start with some background. How to the boundary between physics and mathematics and what we're trying to achieve. Then I'll introduce a model, the activated random walk model, some version of it, and then state some of the results regarding the phase transition of these models and some other results, and describe some of the main tools that we use. Then I think we have time to also explain the main ideas that, without entering details or getting too technical, the main type of arguments that we use in this field, and conclude stating some of open problems that I think are reasonable to consider in the future. So there will be some overlap with previous talks. There was a talk by Chris Hoffman yesterday, and there's the course by Lionel Levine, but I will try not to make this #1 mistake, which is assume that everyone was present and was attentive to the previous talks and just continue from where they started, because if you do this, you'll be leaving behind already some people at the very first minute, and everybody knows you should never leave anyone behind before the 7th minute. So it will be repetitive, so we will be patient, but also I will be saying a few things that Lionel already said, but with my words. So the background, the physics, mathematics background of what we're trying to do. So the context is this of non-equilibrium statistical mechanics. So for the mathematicians, equilibrium, non-equilibrium means typically a Markov process or some process which either has not yet reached stationarity, or it's reached stationarity, but stationarity doesn't mean physical equilibrium. So equilibrium, in the language of for probabilists and Markov processes, it's when it's stationary, but here equilibrium means really physical equilibrium. So one example would be you consider n sites forming a ring, and then you do simple exclusion process on this ring. So we know what the invariant measures are. There will be IID, Bernoulli configurations. This measure is invariant. It's stationary. However, it's only equilibrium if these are symmetric walks. So these particles, they are doing what particles like to do. They're doing their Brownians, hitting other particles, but they're doing what they normally do. If it's asymmetric exclusion process, you still have the same invariant measure, but that's not equilibrium. You have this permanent motion of particles rotating, net flow of particles rotating clockwise. And turns out then it breaks down most of the tools that have been developed in mathematical physics for equilibrium systems. There's no notion of temperature, there's no notion of many things when we are in non-equilibrium. So we're trying to understand the critical phenomena. As Lionel said already a lot in his first lecture, critical phenomena is things that we do observe in nature. Heavy tails, very large events from time to time, of atypical size, large fluctuation, long-range correlations. So I don't think to this public we need to say a lot of what critical phenomena is. And also, so the mathematical challenges that come with this type of question, that is exactly, these are systems that are non-equilibrium and also conservative. I will say more about that soon. So here's a description of critical phenomena as we want to see. So there's some parameter, beta, it could be p, it could be lambda, there's some parameter, and there's a system. The system behaves in some way when that parameter is smaller than something, and as it reaches a certain parameter, it will behave very differently at that parameter. So then you see long-range correlations, random events at the macroscopic or some mesoscopic scale, and very wild type of behavior. And then as you cross that value of parameter, what the system is doing now will be completely different from what it was doing before, but very similar in the sense that it's, again, all very well behaved, short-range correlations, everything nice, sweet, and predictable. And so this criticality is what can help explaining why we see these self-similar shapes and these large bursts with heavy tails distributions in nature. But of course, it doesn't explain why we can actually see this happening, because this one parameter here, it has measure 0 on the space of parameters, so it's unreasonable that a physical system would be there. So of course, we want now to understand how the system finds criticality by itself without being bound to a specific parameter. So this, in the late 80s, was introduced in the physics literature, this concept of self-organized criticalities, systems that find a critical point all by themselves. And it is still a bit mysterious how it happens. But a decade late, or a little more, some other physicists made a claim that, well, typically, or at least if we restrict the notion of self-organized criticality to systems that are in this non-equilibrium stationary state, that all the examples or the relevant examples, could be immediately related to examples of a system where there is a parameter, there is an ordinary phase transition, so we could shift the attention to understand now how this system without parameter can find the critical state for the conservative system, for the system with a parameterized system. So to make this a bit more precise, here's the notion of driven dissipative dynamics. So there is this box, this big box, or it can be a table of throwing grains of sand to repeat the analogy that has been made. So there's this plaquette here, I call it lambda, and we're bombarding this with some mass, some material, some particles. As the particles arrive there, they may cause something to move around in that plaquette, some activity there. And we have an open boundary condition, so when a particle leaves this box, the particle is killed. And so why is this called driven dissipative? Well, driven is that we are, from the outside, forcing something onto the system, and dissipative because eventually the system is dissipating this input through the boundaries. And what you observe in practice is if you start with this large box empty, and you inject particles one by one, and you inject them very slowly so that it has time to stabilize before you inject the next one, you see basically this graph. So you inject a certain amount. As soon as that amount you inject is more than some parameter times the size of the box, of course, it has to be proportional to the volume of the box, then it will no longer be able to retain the mass that you're injecting, and it will start to self-balance. So whenever the density is slightly more than this parameter zeta c, I'm calling here, then it's more easy for the system to dissipate, and if it's slightly under that density, will be easier to accumulate mass. So as soon as you reach this point here, then what you see from now on will be an ergodic process that is stationary, and its state has all these features that we associate with criticality. So then how does this relate to the fixed energy model or fixed energy model in infinite model? So let's, in infinite volume. So that will be the critical state. So we consider a conservative system, so there's no dissipation, and you don't inject anything on it, so it's not driven either. So it's just a space translation invariant system on some space where there is some dynamics there, where you enforce the same dynamics that in the bulk here make this mass accommodate itself. And then this system, now it has a parameter. What's the parameter is how it starts. You start the system with a certain density of mass, and so this system undergoes a phase transition in the sense that when that density is smaller than a certain parameter, the system goes to an absorbing state. Absorbing state is when all this mass is standing still here somewhere. And if the parameter is larger than that, then this activity in this system will persist forever. So I was giving this talk just maybe 2 years ago, and then I was immediately stopped by someone saying, you know, Leo, this picture here has been disproved. Because I made some bold claims about this picture. I said, this thing increases. Well, I did not say, but it increases with slope 1, which means that these tiny bits of mass that you lose on the boundary before you reach critical density is negligible. It really, as the block gets larger and larger, this thing increases with slope 1, it reaches a parameter, it immediately becomes stationary, critical state, and will be now slope 0. That's simple. I said, well, this has been disproved, and my response was, how has this been disproved if I have not even specified what's the mechanism here for these particles to accommodate themselves? So yes, it has been disproved by this group of people in case of the deterministic sandpile model. Okay? This is a very famous paper by Enfei, Lionel Levin, and Dave Wilson, where they prove that indeed the graph does not look like that, and there's a lot more going on in the deterministic sandpile than just that, which, so in some sense, it has this anomaly that it takes so long to mix that by the time you reach that state, it still hasn't been able to find the critical state by the time you reach that density. And at the very end of that letter, they already give a hint to what comes after. It is, well, many people already, as soon as they posted the preprint, responded to them, saying, well, we should include now some randomness in the toppling. This toppling procedure is not really a good one to represent self-organized criticality, or at least not in the more straightforward way we would like to have. And indeed, 2 months later, again in the physical review letters, there is this one-page reply by a group from Korea saying, well, we know this doesn't happen because the toppling mechanism there is not very good, and in a broad sense, it's ergodicity does not hold, but let's interpret ergodicity here in some broad sense. It's just this model is not good enough for mixing things of a configuration. Okay, this is just a comment that will go back there later during the talk. So let me move on to now, or down to the ground, specify a simple model, and the model we'll be working with during this talk today. So the model is the model of activated random walks. So activated random walks, you can think of it as a type of sandpile, except that the stabilization rule is you send all the particles in a site to neighboring sites chosen at random, independently for each particle, except the last one. The last one, you have a small probability of retaining that particle, and if you retain that particle, you stay there indefinitely until maybe some other particle comes, and then it's back into the game. So you don't lose mass, but you put those particles in this passive state where they are not jumping. So let's here describe it now as a continuous time particle system. I'll insist on this description. You can say this is a kind of obsolete because now we understand to just do these stacks, and these stacks tell you everything. They may not tell you exactly everything, and it may be convenient to use this description. So let's switch to the language of interacting particle systems. So what I'm defining here is an interacting particle system. So you have a graph, and I care about ZD mostly. So there's a graph, and at each site you can have a certain number of particles. So there's no exclusion rule, like in the exclusion process, for those of you who attended the colloquium. And you see there's no exclusion rule, so this site here has 3 particles, this one here has 5 particles. And the particles, they also have some color. That color doesn't stay forever, it's just a temporary state. So the particle being blue means the particle will stay there, do nothing. And the particle being red means it will do some continuous time random walk. The rate We can choose it to be 1 because we are mathematicians. We always rescale time so that one of the parameters is 1. And what the red particles do is jump at rate 1 independently of everything else. And except that when they are alone at rate lambda, they can become blue. If they are not alone, there is a Poisson clock that rings at rate lambda. The clock will tell them, well, you should become blue, but the particle will try to become blue and not become blue because there's another one at the same site that will activate it immediately. So you don't see that transition. This is the transition. So an active particle will always wake up a sleeping particle immediately. So this is an interacting particle system. The interaction is only this last line here. Active particle activating a sleepy particle. Apart from that, the particles are each one doing what they feel like, and they don't see the rest of the particles. Is it clear what this system is doing? What is this? So I'm just describing the evolution, not where we start from. Is it clear, the rules of evolution for this particle system? Yes? Yes, it can jump to a site where there is a sleepy particle. Yes. Yes. Exactly. Yes, it's immediate. The activation is immediate in this model. Yeah, that would be very convenient. Yeah, exactly. So maybe at rate 1, the clock is ringing for this particle. When it rings, the particle with some probability will jump here, with some other probability will jump here. If it jumps here, then the other one wakes up immediately. Thank you for the question. Better, yes? More questions? Yes. So the question was, now we have 3. Each one is jumping independent of the others. So in this description as a continuous time particle system, at rate 3, something happens at this site, which means some particle will jump out. Because each one, independently of the others, has a clock that rings at rate 1. Sorry?
Yeah, sorry to interrupt. So I've been told by our AV team that when you are asking question, it is not being recorded. So in asking question, please either use the mic or speak a bit louder. Okay, yeah. Sorry.
I can just repeat
or
the
you
question.
can repeat that.
So how is this different from the contact process with diffusion? That there is this spontaneous transition from active to sleepy. So you infect other particles, but they heal, and when they heal, they don't move. In that case, yeah, you can think this is just a particular choice of parameters for a broad class of models that sometimes are very well related and sometimes have nothing to do with each other. They just have a common description. Okay, so assumptions that we'll make about this model. First is that the jumps are only to nearest neighbors. And at time 0, so I just explained the evolution, not where it starts from. At time 0, each site, independently of the others, will have a Poisson number of particles, all active, all with the same parameter, the parameter zeta. And so they all start active. And this parameter lambda, which is what was lambda, the rate at which a particle goes to sleep, is a number which is positive. If lambda was 0, you would have the frog model. Well, in this case, since they start all active, you actually will have nothing. You just have a bunch of independent walks not talking to each other. And equal infinity would mean a particle sleeps immediately if it's alone. And that, in some sense, is equivalent to what is called, for whatever reason, internal DLA. Which is a model where you launch a bunch of particles and they stop as soon as they reach an unoccupied site. So they will occupy it and stay there forever. So this model is in some sense equivalent to internal DLA if lambda equals infinity. And before someone asks, why am I making these assumptions? because I will be quoting results from a dozen different papers. They each one have different assumptions, and so that we can state them all in the same framework, I make these fairly broad assumptions. So, first question we ask about this model is the absorbing state phase transition. So, two things happen. Fixation means every site, the state at that site will eventually, after some random time, which is not Markovian, but some random finite time, never again switch states, will be either empty forever or occupied by a sleepy particle forever. That is fixation. Where activity is the opposite. For every site, that site will be visited infinitely many times. Of course, by infinitely many, I mean unbounded times, not because there are infinitely many times within a 1 second interval. That's not what we mean, of course. So the first thing is you cannot have both. Yeah? If some site somewhere is activated infinitely many times, the whole space will be visited infinitely many times. So you must have either one. And another thing is you cannot have with probability 1/3 the system fixates and with probability 2/3 the system stays active. Now there's a true dichotomy here, which is either of these two will happen with probability 0 and the other one will happen with probability 1. So now, given the specification of the system, which has this jump, there's a dimension. Okay? Your space has ZD for some dimension. You have some jump distribution, which can be symmetric among nearest neighbors, or it can be something else. And given now the two parameters, the initial density and the sleep rate, this determines whether the system will fixate or stay active. And there's some monotonicity here, which is if for some pair of parameters the system stays active, then by decreasing the sleep rate or increasing the density, it also stays active. Or said otherwise, if for some state, if for some pair of parameters the system fixates, then by increasing the sleep rate or decreasing the density, it also fixates. It's not obvious at principle. In principle, we'll discuss a little bit why it's not obvious. If you think it's obvious, it's okay. Why you have this monotonicity property, I guess you need the abelian property to argue that it has this monotonicity. So, but because of this property, then necessarily there is a curve that only goes north and east, a continuous curve that separates this parameter space into two regions, red region, blue region. In principle, this curve could be completely degenerate. It could just do this and this, or other things. But immediately from monotonicity, we get existence of such a curve. And so what is the prediction? Prediction is that the curve looks like this. So I'm putting infinity here. So of course, there's no scale in this graph. It's just an illustration. So as you make the sleep rate higher and higher, you're able to accommodate more and more particles and still find an absorbing state. That's why this blue region gets wider and wider as we increase lambda. And you can do it all the way up to 1. You cannot do any more than 1. And why is 1 a special number? That's a feature that's specific to this model. Why 1? 1 is how many particles you can accommodate in one site at most. And a particle to sleep and never move again takes one site for itself and cannot share it with others. So this is the number 1 here, is how many particles at most we are able to accommodate per site. Yes? You can. So first, here there's no slope because this is completely out of scale. Okay, this is something to be interpreted in a broad sense, this shape here. Okay, I'm even fitting infinity in the board. You can talk about the asymptotics of what this curve looks like here and there, but even more basic features. The basic feature is that close to this point, you have both blue and red. And close to that point, you have both blue and red. Or a weaker statement that would be a consequence of either two is that there's some point here where it's red. It cannot be that it's blue all the way up to this line. That's a prediction. And it cannot be red everywhere either, except for density 0. That's also a prediction. Okay? So the asymptotics is an interesting question, but more basic question is that you get states with arbitrarily low sleep rate that are still active as long as the density is small enough. The other way around. You can have the arbitrarily small density. If you make the sleep rate small enough, the system manages to stay active. So these are the predictions in terms of what this critical curve looks like. And now here is a bold prediction that this critical parameter zeta c, that we know it exists simply by monotonicity. If you have Poisson parameterized by zeta, you increase zeta, you can couple this, and it means you're just adding more particles. And now I'm saying the zeta c is just a number, it's well defined, and it doesn't care about whether you like Poisson, geometric, or Bernoulli. It's one number, it just depends on how much mass you have in your system. That's what determines fixation against activity. And that's a feature that we really like about this model, and that makes this a very good model for that previous graph I was showing before. Injection, retention. The deterministic SANDPILE does not have this feature. The stochastic SANDPILE does not have this feature either. What else? So at the critical density, the system should not fixate. Well, there is one exception. It's lambda equal infinity and initial condition deterministic, everybody equal 1, so everybody goes to sleep immediately and nothing happens. And that's the only exception. So it should not fixate. We should see power loss, bursts of activity with heavy tails, and some interesting scaling limits there. So these would be the predictions for this model. Well, we can make more and more and more predictions, but I think this is enough material for us mathematicians to work with. Sorry. So is this curve continuous? We don't know. Actually, you see that we know much less than that. That's the prediction. The prediction is the dynamics of this system is good enough to mix the material that you have, the amount of mass that you have, so that in the end it doesn't care if you started with Bernoulli, geometric, Poisson, or whatever distribution you like. You will be shuffled, and they will, if one fixates, all of them fixate. If one of them does not, all of them don't. So is this a continuous and strict monotone? The answer is yes. Can we prove that? No. For all dimensions, for all jump distributions, yes. Okay, do you have more questions about the predictions? Is it clear? Do you have questions? Come on, children, don't be shy. Ask your questions. Questions? Okay, you sure? Okay, so what are the difficulties in analyzing this model? So the first difficulty, at least that was the difficulty 10 years ago, is that this model is not attractive. And attractive means that this as described as a particle system, as we did, the continuous time particle system, attractive means a system where the more particles you have, site-wise. And here, the more particles you have, the more they activate each other. When they activate, particles go away. They go away, the less particles you have, the fewer particles you have. So it doesn't preserve monotonicity in the continuous time evolution formulation in terms of comparing configurations site-wise. this has been overcome, so this no longer is a real difficulty. So we use other constructions and other approaches for the system rather than the usual Harris construction, which I'll comment more later. And the one very big difficulty that you see to obstruct all attempts to make mathematically rigorous theorems about this model is the conservation of particles. Which means if you're trying to show that there will be fixation, then you need particles to organize themselves in some way and fixate. And now those particles are still there. So you always have this to keep track of the things you see. They don't disappear like in percolation or Glauber dynamics phrasing model, contact process, etc. Percolation, something happened very bad on a box. As soon as you find the path around it, you don't need that box anymore. And here you don't have that. You have a problem. That problem will be there for a long time until you can get rid of it in some way. And if I want to make this claim more precise, it's this conservation nature. It rules out what in statistical mechanics people will call energy versus entropy type of arguments in a broad sense. In a broad sense would be what's energy versus entropy. Entropy would be you find some way to enumerate how things could go wrong in your system. Once they have been properly enumerated, or you can do a lot of overcounting, once you've done this, then you punish the bad configurations by tuning some parameter very harshly, close to 0, close to 1, to infinity, whatever it is. You punish the bad configuration so that in the end you can show that they won't happen because they have been already enumerated. I think the canonical example would be a Pyre's argument in percolation, where you show there is a supercritical phase in percolation by showing, well, if there is no infinite cluster, there is a contour that's blocking the infinite cluster. You can enumerate the contours. You can punish them by tuning your parameter very high. So let's call all these types of arguments energy versus entropy in a broad sense. And we basically don't have this in this model exactly because of conservation of particles. Particles can reactivate each other in so many ways that finding, enumerating all the ways in which things can go wrong. Wrong means not what you're trying to show, the opposite. So far seems basically impossible. There's a partial progress in that direction. I'll comment on that later as well. So I will now state some of the results that have been obtained. So there's slow, steady progress in this field in the past 10 years. So, and the list keeps growing, which makes us happy. It used to be very short. List of people who contributed to these results. You see their names also abbreviated as I state. So statements of results, instead of coming with theorem in boldface and a bunch of notation, this is a theorem. Theorem says for any density less than some explicit function of the sleep rate, the system goes to an absorbing state. I'm using the years of archive, so this paper was not published in 2008, but there will be a lot of crossover that will mess up with chronology, so I decided to use archive years here. So this was 2008 and 2014. If the walks are biased, then there exists a active phase. So qualitatively is a reasonably complete picture of this critical curve. So it means this critical curve cannot have a horizontal segment here or here. So combining these two results, the critical curve starts at this point, but immediately enters this region. And so there's no value of density below which you always have fixation, for instance, no matter the sleep rate. So this has been ruled out for biased walks in one dimension. Is it clear? You understand what are the two theorems I'm stating here? Is it clear? So now, if one dimension but unbiased, turns out it's harder. So for fixation, the same result works. For non-fixation, it took a lot of time. So there is this remarkable work by Riddhi, Shishendu Ganguly, and Chris, where they show for symmetric walks that there exists this phase here, meaning for any density, positive density, if lambda is sufficiently small, the system stays active. In this joint work with Amin Asela, Bruno Shapira, and Perla Suzy, we've been able to reproduce their proof, just pushing it further in a few parts, and get something that is qualitatively the same. So there's nothing new here, except that when the density gets smaller and smaller, our lower bound for the critical density now matches with an upper bound that you can get from this joint paper with Vladas and myself. So showing that lambda c is bounded between two constants times the density squared. No, we just have upper bounds and lower bounds. When I say they match, they're still off by a multiplicative constant. Okay? So it's just the exponent here that we found. But since I said that this graph is out of scale, when I show them with same slope here, that doesn't mean anything. You can think slope, this is the log-log graph or something. Yes, it can be told from simulations, indeed, but we are, I'm giving this talk from the point of view of a mathematician. We love the simulations because they tell us what happens, but we want to prove that with epsilon and delta. So when I say we don't know something, it means we cannot prove it. Maybe we know it, and we really know it, we just cannot prove it. So all the predictions are things that we know, they are true, just there's no mathematical proofs that they are true. Yeah, of course you can find the curve with simulations. Yeah. And there is another paper by the same authors, Riddhi, Shishendu Ganguly, and Chris Huissier with Riche. How do you pronounce Riche? Riche. Where they show that on this region here, if you start your model not on the infinite volume now, but on a large ring, a large circle, a discrete circle, it takes a very long time to stabilize. And if you start here, it takes a very short time. So this Chris already stated these results yesterday in his talk. So let's move on to higher dimensions now. So in higher dimensions, we have more theorems. Why? Because the progress were more partial results and slower. So existence of a absorbed phase was first shown by Vladas Sidoravicius and Augusto Teixeira, using renormalization arguments. Those of you who are familiar with renormalization arguments will understand why I plotted so thin here. And then Stauffer and Taghi proved the same lower bound that we had in one dimension for the totally asymmetric case. They show in any dimension. Then for the case of biased walks, this same argument of Taghi from the first slide can now still be adapted to higher dimensions, but to give something more modest. It just says there exists some non-trivial region of non-fixation. It was extended by Laurent Tournier and myself by introducing a new criterion for non-fixation, but this is still the biased case. And in the same paper by Stauffer and Taghi, where they show fixation on this region, they also show non-fixation in the unbiased case, in the symmetric jump case, for low enough sleep rate, but only in dimension 3. So from this graph, let's be clear, this result here is only for biased walks. This result here is only for dimensions 3 and higher. So let's be dramatic here. If it's 2 dimensions, unbiased walks, this is what we know so far. This is a desert. No single proof that the system stays active. Take some density ridiculously close to 1, sleep rate ridiculously close to 0, show that the system does not fixate. There's no proof of that. And now let's move more to the optimistic case. There's one extreme version of this dynamics, which is totally asymmetric walks. So particles, when they jump, they only jump to the right. So the jump is deterministic. So deterministic jumps, you can already tell it will be a completely different universality class in a strong sense. And so for this model, we can tell exactly what the critical curve is. There's a simple expression for it. And we can even say interesting things that happen on the critical curve. So this would be a, let's say, integrable or exactly solvable case. So there's this paper by Manuel Cabezas, Vlada Sidoravicius, and myself, where we show what the curve is. Well, show what the curve is. This is a three-line proof. In fact, this had been known for a long time, since the prehistory times, before any of these papers appeared. Vladas was already discussing this problem with Chris Hoffman, and they already kind of knew this, but this was never written. So the shape of the curve appears in this paper with Manuel Cabezas and Vladas, and the fact that we don't have fixation even when the density is 1 also appears in that paper in any dimension. And now on the curve, we can study some scaling limit in some sense that we'll get back to that later. So this is results regarding the phase transition, regarding where does this critical curve, where it is, what does it look like. So before we go to more results that are not of this type, so discuss a bit what's the constructions you can make for the system. So first you can write down a generator and use spectral theory to show that the system exists, but then there's nothing really useful you can do with that. If you want to really put your hands on the system, you better construct it explicitly so you can work with that. So you can construct particle systems using Harry's graphical construction. If you've never heard of it, you can ignore the next half a minute. So Harry's construction is, at each site you put on a real line that represents time, you can put Poisson processes with marks, and the time indicates when your continuous time reaches that point. The mark will tell you what happens with that site. It sends a particle out. So if it's easy model, some spin may flip from a plus to minus, etc. So far, this construction has not proved any useful for the activated random walk model. Then we switch to the site-wise construction. So we put stacks on a site, and then each time something will happen on a site, in order to decide what has to happen, so the randomness has been, let's say, realized beforehand or sampled beforehand, you just get the first instruction from that stack and apply that. So particle will jump to north, particle will jump west, particle will go to sleep, or at least try to go to sleep. And then you have this sequence. Of course, you want this sequence to be random of instructions at each site. And the fourth time something is going to happen on that site, you just read what the fourth instruction says. And another construction is instead of putting the randomness on the sites, you can put the randomness on the particles. So at time 0, I think many of you don't know what a videotape is. At time 0, particles are given a videotape of their life. And that videotape is a continuous time random walk with some beep, some Poisson beep, that at rate lambda you hear some beep. When it beeps, the particle goes to sleep. Those pause on the videotape, so it doesn't keep going on that videotape, or the life plan of them, until some other particle activates them, and they are reactivated, and they continue performing the plan they had from the beginning. This construction can also be quite useful. I hope we'll have time to get there. So from the site-wise representation, that in most of the mathematical literature will attribute it by Diaconis and Fulton, but probably these ideas had been around before. That's exactly when you put the stacks, and then a systematic way of how you use these stacks. This first appeared in this paper by Vladas and myself, where we relate site-wise representation to the continuous time dynamics and do this general framework of looking at the odometer, introduce a toppling procedure, show that this toppling procedure will imply the properties that you want to be satisfied. And then for the particle-wise construction, there is this paper by Gideon Amir and Ori Gurevich, where they show that non-fixation of a particle implies non-fixation of a site, and that is very convenient because now we can use many tools. It implies mass conservation. And, well, except that this paper by Gideon Amir and Ori Gurevich, it assumes that there is a particle construction for the system. And when the first time we wanted to actually use this result, we had to prove that you can make sense of what is a particle-wise construction, prove that it's well-defined. Once it's well-defined, now you have a completely different set of tools. You can play with the particles, ask what happens if you remove one, add one, resample them, use properties of ergodicity, mass conservation, etc. And then we also introduce a new criterion for non-fixation, but I'll say it, let me skip this. I'll say it later. So these are the main tools that have been used. And now a property that we cannot show on the graph, so next results I will state we cannot show on that parameter space, is this one. So uniqueness of the critical density, that statement I made earlier that may have caused some discomfort. And it's a theorem. Given the dimension, the jump distribution, and the sleep rate, there is one number. I call that number zeta c. I think now we don't need to use stars and hats. And there's one number, and you don't need Poisson IID anymore. You give anything that is ergodic with respect to spatial translations. If that thing has a density above zeta c, it stays active. If the density is below zeta c, it will go to sleep. Sorry? P is the jump distribution. So P, thank you for the question. So P is a probability distribution on ZD. A probability distribution on ZD. So once you know the jump distribution, you know the sleep rate dimension, then there is a unique parameter, and that's what I was saying before. It doesn't matter if it's Bernoulli, Poisson, geometric, whatever you want. If the density is smaller, it fixates. If larger, it stays active. If the density is exactly equal to zeta c, then we can't prove. It should stay active. We can't prove. Yes? So we only know the critical value if P is completely degenerate. The particle jumps always to the right. No condition on P. It works on any unimodular, amenable graph. Let's say you want to go high or you want to stay on ZD. Any P. It does apply to degenerate walk. So, yeah. So the assumption on P is that, well, it doesn't depend on where you are. That your jump distribution is translation invariant. Yeah. It can be long range, it can be anything. It's just mass conservation type of argument. It doesn't matter. Particles are going very far, you can still keep track of them. So this is it clear what the statement is saying? I try not to use too many words. Sorry? Ergodic initial states. So your configuration is denoted eta t. Okay? So eta 0 has distribution, let's say, nu. So a nu, what is nu is a measure on the space of configurations. This measure nu, we assume that it's invariant by translations of your graph. Not only it's invariant, it's ergodic in the weakest possible sense. So it assigns probability 0 or 1 to observables which are completely translation invariant, not translation invariant in each direction. So I mean, ergodic is the least thing you could ask for a measure. Otherwise, the measure could be with probability 1/2, you have everything crowded. With probability 1/2, you have nothing at all. So ergodic is the least you could say about some state. Yes, makes sense? It's clear? So what do we get from this theorem? First, of course, we can drop the previous IID Poisson and not talk about Poisson anymore. Now we're really just talking about densities. Second, all these papers I was citing before, the theorem maybe they had some requirements that would make them easy to work or make it possible at all. Now we can drop all the requirements. Whatever proof you have for one particular initial distribution gives a result about zeta c that doesn't matter the distribution in the end. And if we go back to this discussion of the self-organized criticality description, so it contributes to this discussion of some models are very good at mixing particles and some models are very bad. And we can now dedicate effort in understanding how bad they are, why they're bad, in what sense are they still a little good or not. Or we can consider a model that is maybe a little bit harder to analyze, but has a more straightforward relationship with self-organized criticality, if that's what you're looking for, of course. So scaling limits. Vladas, I think you will want to see this. So scaling limits, I would consider one-dimensional process. The one I was talking about before, directed walk. So the walks only, if the clock rings to jump, it jumps to the next site. That's all they do. So this is, we can say it's an integrable system. In the case, it's basically exactly solvable. So we consider some IID initial condition. Now IID matters because I'm not considering fixation or activity anymore. I will say something about the system. So IID initial condition with the critical density, and that's the expression for the critical density. And what we're looking at, what we're going to look at is, you do the site-wise construction with stacks. You stabilize a long interval that ends at a certain site, let's say the origin, and you count how many particles cross the origin, and call that Cn. Is it clear what is the process we are looking at? And then as you increase n, you have a larger domain to stabilize, so we can think this silly, let's give me a, the site-wise construction is the one where you put stacks in order to stabilize. So if you, now when you look at a bigger box, you're still using the same sample of stacks to determine Cn. You can think, here is us observing how much snow is going down this mountain, and it's snowing, it's drops of snowflakes at the exactly the critical amount is falling on this mountain higher and higher, and then we are counting how much we see going in front of our window. Of course, there's a rock here. We are very safe away from that avalanche. Okay? So if you do a simulation, this is what it looks like. So this is for n equal 100,000, 10 to the 5. And this would be the order square root of that. So this is just a process from natural numbers to natural numbers, counting how many particles go through the origin. So I will now plot same simulation on the left, another one on the right. Can we say these two are similar? Could they have been sampled from the same process, from the same prescription? I think they look similar. I hope you look similar, otherwise you're ruining my surprise. This second simulation here is just a zoom on this first window of the first simulation. So indicating some self-similarity of this process, which of course you expect to have self-similarity if you have a scaling limit. And that's the theorem, that this has a scaling limit. So if you now look at this process, Cn, discrete process, the integer valued, indexed by n, you rescale it in the diffusive way. Then there's some constant. We don't care about constants. It rescales to a constant multiple of this process that I call C calligraphic. It has some parameter rho. This parameter rho, I do care about it because it's not just multiplying by something. It really makes the scaling limit be very different. So we can give an explicit description, construction of this process C rho in terms of a collection of Brownian motions that are correlated, and when they meet, they coalesce, and they are reflected at 0, etc. What is a nice feature of this process? It's a pure jump process. So meaning, even if here there are very nearby jumps, their distance is still macroscopic. There's no accumulation of jumps in this process. Well, that's not in this statement. And you don't fill the gaps. You do macroscopic jumps in the vertical scale here. So it's a pure jump process that we construct explicitly. And what is this parameter rho here? Rho will be the ratio between the variance of the initial configuration and the variance of a Bernoulli with the same average. Okay. This is the variance of a Bernoulli, which is also the variance of this the indicator variable of whether a particle goes to sleep or jumps. So this is the variance. And then my initial condition has exactly the same density, so the variance will be at least the variance of a Bernoulli with the same average. So if you divide both, you get a number which is between 0 and 1. And that number, that parameter will describe what this scaling limit looks like. So here's for different values of this parameter, as it ranges from 1 down to 0, what it looks like. It becomes less and less jumpy and more filling the gaps. Until in the limit, when it's 0, then it's a continuous process. In fact, this is just the running maximum of a reflected Brownian motion. So in this one, we could still, this appears in a paper back 2013 by also with Vladas and Manuel Cabezas. So it rescales to a process which is not pure jump, but this is still singular. So all the increase happens in a set of measure 0. We can still maybe say these look like avalanches, but I think we like a lot more this one, where it's real jump. So we can really see, say, a macroscopic amount of snow passed by the window just by one extra snowflake that we dropped there in the site n+1. So I will try. If I have time, if not, I can do it just for you. Okay? So I will make some notes without any details. Oh, yes? Yeah, you compress space by epsilon, you compress time by epsilon squared. And then there will be a multiplicative constant depending on the variances. So some selected proofs. So let's first, what is a toppling procedure? So most of the proofs of these results that I stated before, they rely strongly on the abelianness. Abelianness is like, it entitles us to decide on which order topplings will occur. So we can write a toppling procedure, which basically is a prescription of which site to topple depending on what you see, or depending on tossing an extra coin if you want, even depending on things that haven't happened yet. You can look at what these checks of instructions are, if it's convenient. And so let's define what's the odometer. The odometer, once this stack of instructions is fixed, the initial condition is fixed, the odometer just says how many times will you topple site X if you stabilize this box V. Okay. That's the odometer. And what's the criterion for fixation and not fixation? It turns out to be equivalent, but it's not entered the details why it's equivalent. It is, as you make this box larger and larger, does this odometer tend go to infinity in probability, or does it stay tight in distribution? There's a dichotomy here. Either it stays tight or it goes to infinity. Okay. So which means we can make this box larger, take this limit in K, and this limit can only be 0 or 1, so it's very convenient. If you want to prove it's 0, you just have to prove that it's not 1, and vice versa. That's, we are not going to use this, but this is condition B, which means this odometer stays stochastically bounded by some random variable as you make the box larger. And U means unbounded, it goes to infinity. Another criterion is the one I mentioned before, is quite different because here we are talking about probabilities and we have to handle probabilities to show that something occurs or not. So now let's do the following. When we stabilize a box V, and ignoring what's outside, count how many particles exit the box. Call that MV. So the criterion is, as you make this box larger, is this expected number of particles that leave the box proportional to the volume of the box. by some positive constant of proportionality. If this is true, then the system stays active. We call this condition E. These are the main tools. So let's give a brief sketch of how you would use these to prove something. So there's this, by Stauffer and Taggi, they show that zeta critical is at least lambda over 1 plus lambda always, for whatever graph, whatever jump distribution, etc. It goes as follows. Suppose the system does not fixate. So if the system does not fixate, then you know the odometer goes to infinity in probability. In particular, if this is a site, I'm calling this the site O, the origin. If there is radius is large enough, then mv of O will be greater than 1 with high probability by taking this R large, just using the previous condition that characterizes non-fixation in terms of odometers, which by monotonicity in the volume, it can be any box that contains a ball of radius R around the origin. That is still true. And now the observation they make is the following, is the Toppling procedure this is the common feature of almost every proof, is that they specify a Toppling procedure. The Toppling procedure will have 2 stages. In the first stage, you keep one active particle at the origin. If it has 2, you send 1 away, but if it has 1, you keep it there and stabilize everything else. That's the first stage. And the second stage, you just finish. Stabilize everything now. So the second stage can be empty if there's no particle at the origin. It can be just a single step if there's a particle and it goes to sleep. Or if there's a particle and it does not go to sleep, you can activate particles that will activate particles again, 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 again. So the second stage can be many different things. So the main observation, the key observation, is that the probability that after you stabilize, you have a sleepy particle. You have a sleepy particle at the origin after you stabilize will be at least lambda over 1 plus lambda minus something small. It's lambda over 1 plus lambda times the probability that this event occurs. Because if in the first stage you have a particle at the origin, the probability that the second stage will just be 1 toppling, particle sleeps, that will be lambda over 1 plus lambda, which is the ratio between the sleep rate and the total event rate. So you have this probability, and this applies to any box that contains a ball of radius r around the origin. From there, you can now look at a much bigger volume, and you can consider the set of all sites that are at distance r from the boundary, and then you can ask how many particles you have sleeping there in the end of stabilization. Well, the joint distribution of this can be a very complicated thing, but if I just want the expectation of that thing, expectation is linear, so I'm just summing a bunch of these events. So this expectation of this number will be more than lambda over 1 plus lambda times the volume of this box. By the previous argument. And on the other hand, the number of particles you have sleeping here in the end is no more than the number of particles you had here when you started. And this is zeta times the volume of the box. So from here you conclude if there is non-fixation, zeta has to be higher than that magic number lambda over 1 plus lambda that I wrote there. So that proves the first theorem by Stauffer and Taggi. So another case where we again specify a Toppling procedure with 2 stages. It's following the toppling procedure was introduced by Taghi and simplified by Laurent Tournier and myself with the introduction of this condition on average number of particles. It says the following, if the walks are biased, so you take some vector v such that the walks are transient in that direction, a walk is transient in that direction, and then you consider this space orthogonal to v, or the half space on that side of the hyperplane, and you consider one random walk. They are transient in that direction. You consider one random walk that jumps at rate 1, but when it's below this line, it's killed at rate lambda. A clock at rate lambda can ring at any moment. If it rings, the walk's killed. And then you can write f of lambda as the probability that the walk is killed. And the claim is that the critical density is less than that, and this is what will give this region here of non-fixation that we saw before when I stated the theorems. So, and how do we go about showing that? It's again, we specify a toppling procedure. The toppling procedure will be fix a large box, enumerate the sites ordered according to their inner product with V, and then take the first site, if there's a particle there, move the particle until the particle either exits the box, sleeps before it, or finds an unoccupied site after it, in which case it will not sleep. You leave it there, and then you move to the next site. You keep doing this. Then you count how many particles you left behind in this process. If they exit the box, that's good, because that's what we want to show. You count how many particles you left behind. On average, you leave behind no more than this amount here, because this is exactly what happens to this particle. And so you leave behind at most this amount, but if you started with this amount, so the difference will be a positive proportion of the volume. It has to exit the ball on average, so we're just talking about expectations here. So this simplifies a lot. So we're talking about this condition. We don't need to consider the variance and show that this number will be large with a high probability or anything like that. So this will prove that this upper bound for the critical density. Another argument, which is again uses a toppling procedure, is this paper I mentioned before by Riddhi, Shishendu, and Chris. So it's one-dimensional symmetric walks. So what's the toppling procedure? Or my rephrasing of how they describe the toppling procedure, it's the following. We'll split the particles in 2 teams, orange team, purple team, and we'll ignore the interaction between the 2 teams. So you choose the toppling procedure will be the following. You choose one of the particles at random. If that particle is circular, it means it's active, then you topple it. If the instruction is to sleep, and the particle doesn't have any other of the same team there, then you put that particle on hold. So on hold, I'm indicating by a cross. So since the 2 teams do not interact, so this particle can be on hold, even if there's a particle of the other color there. So on hold doesn't necessarily mean the particle is sleeping. It may be sleeping, maybe not. Circle means the particle is active. So we leave the particle there on hold, we don't touch it, and we keep repeating this procedure. Pick one of particles which is circular, pick one of them at random, topple it. Keep doing it until it stabilizes. So what do we want to show here? What's the goal? The goal is to show that we have a small number of particles here in the end. Most of it will have to exit this interval. That's the main step in proving this. So 2 comments about this toppling procedure is, first, I insisted on the fact that you choose a particle at random to move. Why? Because since we don't know whether the crosses are actually sleeping or not, the outcome, when you stop this, the outcome is not a billion. It will be a billion if you now reveal which crossed particles are actually sleeping or not and finish the job. But if you stop here and just look which one is circle, which one is cross, this is not a billion. So all movements that we are making here with particles, they are legal in the original dynamics, so it's fine. So when you complete this, you just throw away even more particles to the boundary, but the final result is not a billion, so let's make an abelian version of it. The abelian version of it will be, let's rewrite this graph in 2 layers. This will be the orange layer, this will be the purple layer. And now, particles which are here, they are really not interacting because in this new graph of mine, they are even different sides. Okay? How to recover the 2-color process from this process, just collapse it again and add the states together. Another rule is, if this particle jumps to the right, it becomes purple. And if this particle here jumps to the right, it will become orange. So there's these sites here where particles change teams so that one team can keep helping the other again and again. So this changing teams feature, I'm introducing these artificial sites here. I call them buffers. There are no sleep instructions on that site. I'm only using them to hold the particles and tell them when to go there and join their new team. And this will produce the same dynamics. On the end, it's a billion. So we can now use and abuse a billion as we please. Is it clear? So how do we now analyze this, make estimates? How can we say anything about the dynamics here? Well, we'll focus our attention on the odometer only at these buffers, these sites where particles switch from one team to the other. This is the only point where the 2 teams talk, interact. When a particle leaves here, joins a team, which corresponds to a particle that hasn't been here before, so it's purple, and now it's about to become here, so you switch its color to orange. You want to analyze this vector, M1 to Mn, of odometers and say something about it. So you look now at a single block. What was a single block? You have this buffer, you have these sites, and you exit. For a single block, you have the initial condition, the particles that start there, you have the instructions, you can define these random functions, Li, Ri, and Si. I is just identifying the block. The argument is how many particles join this team from the middle. L, R, and S are how many particles it will spit on the right, on the left, or keep slipping inside the domain as a function of how many particles join from the middle. So these are random functions at each block. The nice thing is that each block you have this, of course, this balance condition that the initial, how many particles you had before, plus how many particles you add, is how many particles you will spit out, minus how many stay sleeping. So there is this balance, mass balance condition, and I'm going to rewrite it from the point of view of a new block from the right, knowing only what happens from the left. So this block I needs to send to the left exactly what the balance condition in the site of the left. So it's how many particles the block immediately to the left wants to receive, minus how many it has already received from the left-left block. You have this mass balance equation, so you know whatever this vector of odometers at buffer sites are, it satisfies, we don't know what it is, but we know it satisfies this constraint. So now what you do to completely decouple different blocks is we look at the exponential moment, how many particles are in this region in the end. That's what we want to control, how many particles stay there in the end, so that the accessor has to leave. Look at the exponential moment, because of course exponential of a sum will factorize as a product, and since we have no idea what the odometer is, we don't know what to do with this, why don't we just sum over all possible vectors of odometers, just imposing this condition on them? So, and that's what they did by imposing this condition, and you summing over all possible odometers, you decouple this expression for the exponential moment, and now you consider the worst case, so that you get independence. So everything boils down to making a single block estimate. Single block estimate is, you forget about this large interval we started with. We have one block. We want to know the output on the left. So when this block gives on the left the exact output where we're requesting it, does it have sleepy particles there at all? If it does, it will increase this exponential moment here. And now you sum over all possible numbers of inputs you give the block, and you control that, and you show that stays bounded by 3. I wrote 3. If it had been 17, it would be just as good. The point is that this number 3 does not depend on how large the block is. If the block is very large, you compensate it by taking lambda very small. And with this single block, you plug it in the previous equation, and then everything will follow from that. Yeah, and this is the last remark I made. If you just have to take lambda small enough. So I guess everyone is tired, so let's just make this one last effort. Go to particle-wise constructions. So some things are proved using particle-wise constructions, and even more things can be proved if you combine particle-wise constructions with site-wise constructions. So in the particle-wise constructions, the particles are labeled. They are no longer indistinguishable. Oh, that's non-physical, but that's just for the purpose of mathematicians proving theorems. Why do you care about labeled particles? Because now we can use mass transport principle. We can say if the particle was born here and died there, we can use that to make arguments based on conservation, etc. And how does it work? So we sample at time 0 the number of particles that will be at each site. And for each particle, we sample, it's a videotape, which I described before, a continuous time random walk with a beep. And the theorem, assuming this construction exists and makes sense and is well-defined, is that a theorem by Ayyer and Gurevich is, well, if a particle fixates with positive probability, then a site fixates with positive probability. Oh, wait. That's not the theorem. That's pretty obvious. If a particle will fixate, it has to fixate somewhere. So this first implication is obvious. Or not obvious, one-line proof. Second implication is not yet the theorem either. Of course, if a site fixates with positive probability, it has to fixate almost surely by the 0-1 law, by this dichotomy between systems either stay active or sleep. There is no half probabilities here. So if a site fixates with positive probability by the 0-1 law, they fixate almost surely. The theorem is that if sites fixate almost surely, then particles have to fixate almost surely. And this, of course, implies the first statement. So these are all equivalent, and that's very convenient. So that's the theorem by Ayyer and Gurevich. So how can we use, for instance, the mass transport principle? We assume that particles fixate. If they fixate somewhere. So you can write a mass transport function going from where the particle started to where it ended, just to conclude that the number of particles that start at the origin, on average, will be equal to the number of particles that settle at the origin, by simple mass conservation argument. What we get from this, well, this number is exactly zeta, and this number cannot be more than 1, because no more than one particle can set at a site. So this already implies that zeta c is less than or equal to 1. So this was the theorem stated by Ayyer and Gurevich, that zeta critical is less than or equal to 1, but their method of proof was in fact more interesting than the statement itself, which is going through these implications. If we want to go a bit further and do some surgery, we can show that if sites fixate, which is equivalent to particles fixate, then the density, in fact, is strictly less than 1. So not only mu critical is at most 1, we know that at 1, there is no fixation, even for infinite sleep rate. So for infinite sleep rate, the critical density actually equals 1, and there's no fixation there. So let's not show the proof, because we're running out of time. So to make all this quickly, how do we show that? If there is site fixation, it means a site has positive probability of being visited by less than 29 particles. which means there's a set of 29 sites somewhere, such that with positive probability the origin is only visited by particles as starting there. Well, we can resample the initial condition at those sites. With positive probability, it will be 0, and on that event, the origin is never visited, so with positive probability, it's never visited. So this expectation is strictly less than 1. Finally, for all this machinery to work, of course, we have to make sense of what a particle construction is. And that's a theorem by Laurent Tournier and myself, where we show the existence of this particle-wise construction. So maybe even harder than show that it's well-defined is to say what it is. So what is the particle-wise construction? You add the particles one by one, and maybe they will affect what you had before, because they will activate some particles, so you have to update the story of what all the other particles are doing, and you do that indefinitely. And show that the future life of one particle will be well-defined through some limit. So maybe, when you start at the first particle, you know exactly what it does. It jumps, it sleeps, finished. Now you add the second particle, so maybe now the first particle jumps, sleeps, but later on it's reactivated, so it jumps a little more and sleeps. Okay? And you keep adding one and more and one more and one more, and updating what's the story, the life history, the biography of the previous particles. And you hope that this will give a limit, that the life of a particle will not change infinitely often as you add more and more particles. There's a subtlety here. We also want to show that this map that takes the randomness into this evolution, this description, is translation covariant. So it doesn't matter in which order you add the particles, roughly speaking. This boils down to showing that for every site, for every finite time t, the number of particle additions that can affect that site has finite expectation. Not really finite expectation, it's bounded in distribution by some translation invariant law and subsets of the space that has finite expectation. And in these 2 minutes that I have left, let's give an idea of how we would go about proving the last statement. So how can we show that only finitely many particles will affect a given site far away? We have a configuration eta and a configuration eta prime, and they differ only by one particle at one site. And I represent configuration, so these are sites. So the star is this one particle that is present in eta, but not in eta prime. I denote it by a star. I don't want to know if this particle is active or sleeping, because, well, I don't even know if this particle exists in the first place, because I'm trying to describe both processes simultaneously. So I represent it by a star, so that balls and crosses are contained in both eta and eta prime for all t, and they are, in turn, contained in the balls and crosses and stars. So we just have to now show that the stars don't propagate too fast to affect what you see far away in finite time. So how do stars propagate? Well, particles affect the system by interacting with other particles. And how can that be? Well, if this particle wants to sleep, now you don't know if this particle is there or not. So now you don't know if this particle will sleep or not. So you replace it by a star. If now this particle wants to jump, well, you don't know if this particle exists at all. If it exists, you don't know if it's there at all. And if it's there, we don't know if it's active, but maybe it is, and it wants to jump. So you create a new star here, but you keep this one here, because you don't know if the particle was active or not. So you keep this one here. And maybe when it jumps, there was a sleepy particle there. So now we don't know if that sleepy particle is sleepy or not, because there's a particle that we don't know if it's there or not. We transform it into a star as well. So all this description depends on how many other particles are nearby, etc. If we don't want to consider that, and we want something clean, and we do an upper bound, and the upper bound will be this event, that this particle wants to sleep, just means a star will replicate. And this happens at rate lambda. Why lambda and not 2 lambda? Because if there is another particle here, then the presence of this particle is irrelevant. This one cannot sleep, and you know it cannot sleep because of these other 2. So it only happens if there is a unique active particle together. So if at rate lambda, this particle replicates, and at rate 1, this particle will create 2 copies on a neighboring site and keep a copy there. So this is a branching random walk. Obviously super critical. This thing grows fast. But the question here is not critical or subcritical. The question here is that the expectation of the number of stars at time t is finite. We even know what it is. It's finite. And the number of stars is, of course, not bound for the number of sites where you have ever seen a star up to time t. So this whole construction with particle-wise randomness is almost surely well-defined. And the subtleties, let's leave it for another moment. And I think I'm over time, so we open. Thank you for your attention.